I am AKB Anjan Kumar Bhuiya from the Department of Mathematics, Vishwabharati. In this module, we will introduce conjugate of an element of a group G and deduce an equation known as conjugacy class equation, which establishes relation between order of a group and order of elements. And this equation will lead us towards the converse of the Lagrange theorem. The idea behind the Lagrange theorem is to partition a finite group G by cosets of a given subgroup H of G. Here we give another partition of G by conjugates of an element. This partition by conjugates of an element is helpful to proceed towards the converse of the Lagrange theorem for non-commutative groups. Our previous results are not sufficient to answer even the simplest question about non-commutative groups. For example, is there a subgroup of order P for every prime P dividing order G? We prove an affirmative answer to the question in the next module. In this module, we introduce conjugates of an element and find a useful relation between the order of G and the order of its center. Let G be a group and A belongs to G. An element B belongs to G is called a conjugate of A in G if B is equal to C A C inverse for some C belongs to G. For example, consider the group S3. We show that 2, 3 is a conjugate of 1, 3. For this, note that 1, 2 into 1, 3 into 1, 2 inverse is equal to 2, 3. Also note that conjugates do not make any sense when G is abelian, since in this case C A C inverse equal to A for every A and C in G. So, A is the only conjugate of A if G is an abelian group. Thus, this notion becomes important, particularly in the case when G is non-commutative. Our first result is that the conjugates give rise to an equivalence relation on G and hence a partition of G. Let G be a group, then the relation rho defined on G by A rho B if B is a conjugate of A, that is if B equal to C A C inverse for some C in G is an equivalence relation on G. For all A in G, we have A equal to E A E inverse and hence A is rho related with A for every A in G. Thus, rho becomes an reflexive relation. Now, A rho B implies that B is equal to C A C inverse for some C in G. Then A is equal to C inverse A C If we denote C inverse by D, then A becomes D B D inverse, so that B becomes row related with A, hence row is symmetric. Now to prove that the relation row is transitive, for this consider A row B and B row C. Then we have two elements x, y in G such that B equal to x A x inverse and C is equal to y B y inverse. Then it follows that C is equal to y x A y x inverse. We get this relation by replacing the value of B in the second equality, and so we have A is row related with C, hence row is transitive, thus row becomes an equivalence relation. The relation row on a group G as defined in the previous theorem is called conjugacy, and the equivalence class of A determined by this equivalence relation row, which we denote here by CLA, is called conjugacy class of A. Thus, CLA is the collection of all elements C A C inverse where C is in G. In the following, we find the conjugacy classes of the elements in S3. The group of all permutations on 3 symbols. Recall the result that two permutations alpha and beta are conjugate if and only if they have the same cyclic structure. So it follows that all 2 cycles 1 2, 2 3, 1 3 are conjugate to each other, and the 3 cycles 1 2 3 and 1 3 2 are conjugates. Thus, the conjugacy class of E is the singleton set containing E only, and the conjugacy class of 1 2 is the set containing all 2 cycles 1 2, 2 3, 1 3, and the conjugacy class of 1 2 3 contains 2 3 cycles 1 2 3 and 1 3 2. Now we establish a relation between centralizer of an element A and the conjugacy class of A. Recall that the centralizer of an element A in G is given by CA is equal to G belongs to G such that GA is equal to AG. That is the collection of all elements in G which commutes with A. Then for CD in G, CAC inverse is equal to DAD inverse if and only if we have C inverse DA is equal to A into C inverse D, and this is if and only if C inverse D is in the subgroup CA. If and only if the left coset of C determined by CA is equal to the left coset of D determined by CA. This shows that two elements C, D in G gives the same conjugate of A if and only if they give the same left coset of CA. In the following theorem, we establish that number of distinct conjugates of A is equal to the number of distinct left cosets of CA in G. Let G be a group and A belongs to G. then the number of conjugates of A in G is equal to the number of distinct left cossets of Ca in G. That is, order of CLA is equal to index of Ca in G. Recall that the index of Ca in G is the cardinality of the set of all distinct left cossets of Ca in G, which is equal to the cardinality of the set of all right cossets of Ca in G. Though we speak number of elements, but in its strict sense we should note that in case of infinite sets, the number of elements or number of conjugates actually means the cardinality of CLA. So, to establish the result, we need to establish a bijective correspondence between the set of all left cossets and CLA. Let us denote the set of all left cossets of Ca in G by script L and define a mapping F from script L into CLA by FGCA is equal to GAG inverse. Since the elements in L may have different representations, so first of all we are to establish that the mapping as we have defined here is well defined. So, consider two elements GCA and HCA such that GCA is equal to HCA. This is if and only if G inverse H is in Ca. If and only if G inverse H commutes with A and gives us GAG inverse is equal to HAH inverse. This is if and only if image of GCA under F is equal to image of HCA under F. Thus, it follows that F is well defined as well as 1 to 1. Also from the definition of F, it is direct that F is onto. Thus, F becomes a bijection and we get order of CLA is equal to order of script L, which is equal to index of Ca in G. These are the 4 equivalent conditions for every A in G. Here we left the proof. The first condition is that A is in ZG if and only if G is equal to Ca, which is equivalent to the condition that the only conjugate of A is A, and this is equivalent to the condition that Ca has the index 1 in G. Using these 4 equivalent conditions, we have the following important relation. First, note that from the 4 equivalent conditions, it follows either A is in ZG or CLA intersection ZG is equal to empty. Now, we prove that if G is a finite group, then order G is equal to order ZG plus sum of the indices of Ca in G, where the sum runs over a complete set of distinct representatives of conjugacy classes which do not meet Zg. Let W subset of G be a transversal for the set of all equivalence classes of the conjugacy relation rho. Then A belongs to Zg if and only if CLA is the singleton set A, and this implies that Zg must be a subset of the transversal W. Then, since union of CLA is equal to G and the CLA are disjoint, we have order G is equal to summation order CLA where A runs over the transversal W, and we can decompose this summation into two parts, namely one part where A runs over Zg and the other part where A runs over W minus Zg. If A is in Zg, then order of CLA is equal to 1. So, the first part of the summation gives precisely order Zg, and the second part becomes summation of the indices Ca in G, where A belongs to W minus Zg, by the result that the number of conjugates of A in G is equal to the index of Ca in G. This particular equation for a finite group G is called the conjugacy class equation of G. This is important because it gives a relation between the order of G and the order of Zg when particularly G is non-commutative. Now, we give an example of a conjugacy class equation. Consider the group S3 of all permutations on 3 symbols. Recall that the center of this group, that is ZS3, contains only the identity element E, and the conjugacy class of 1, 2 contains 3 elements, and the conjugacy class of 1, 2, 3 contains 2 elements. So, the class equation order S3 is equal to order ZS3 plus conjugacy class of 1, 2 plus the order of the conjugacy class of 1, 2, 3 gives us 6 is equal to 1 plus 3 plus 2. Now, as a generalization of the conjugacy relation on a group, we define a relation, namely conjugacy relation between subgroups of a group. First of all, we show that if H is a subgroup of a group G, then for any A in G, A inverse is also a subgroup of G. This leads us to a natural generalization of the conjugacy relation on G. Let G be a group and H be a subgroup of G. Then for every A in G, A inverse is a subgroup of G. Not only that, moreover, we also have H is isomorphic to A inverse. First, we show that A inverse is a subgroup of G. It is trivial to note that A inverse is non-empty. because E belongs to A H A inverse. Now consider two elements alpha beta from A H A inverse. Then alpha will be of the form A X A inverse and beta will be A Y A inverse for some x y in H, and then alpha beta inverse is equal to A X A inverse into A Y A inverse whole inverse. But A Y A inverse whole inverse is equal to A Y inverse A inverse. Thus we get alpha beta inverse is equal to A xy inverse into A inverse. Since H is a subgroup and xy is in H, so we have xy inverse is in H. Thus alpha beta inverse becomes an element of A H A inverse. Thus A H A inverse is a subgroup of G. Now to prove that H is isomorphic to A H A inverse. For this, define a mapping F from H to A H A inverse by F H equal to A H A inverse for all H in H. Then from the definition it follows that F is onto, and by the cancellation properties in a group it follows that F is 1 to 1. Now to show that F is a homomorphism. For this, F H1 H2 equal to A H1 H2 A inverse. Insert A inverse A between H1 H2 and we get A H1 A inverse into A H2 A inverse. Thus F H1 H2 becomes equal to F H1 into F H2, and hence F becomes a homomorphism and we have H is isomorphic to A H A inverse. Let G be a group and H K be two subgroups of G, then K is said to be a conjugate of H if K is equal to A H A inverse for some A in G. Similarly, as the conjugacy relation between elements of a set, it can be proved that the conjugacy relation between subgroups of a group G is also an equivalence relation. Thus, if A is a conjugate of H, then H is also a conjugate of K. Henceforth, we say H and K are conjugate to mean either of them. Recall that a subgroup H of a group G is said to be normal if G H G inverse equal to H for every G belongs to G. If it is not normal, there may be some element A in G such that A H A inverse equal to H, but certainly not. And the collection of such elements is denoted by NH, which is a subgroup of G and called normalizer of H in G. Now we generalize this the notion of normalizer. Let H and K be two subgroups of a group G. Denote NKH to be the collection of all elements K in K such that KHK inverse equal to H, that is H remains invariant under K. Then it is easy to observe that NH is actually NGH, and it follows that NKH is equal to NH intersection K. Let H and K be subgroups of a group G. Now we prove that NKH is a subgroup of K, and this we call as normalizer of H in K. NKH is a non-empty set because E belongs to NKH. Now to show that this is a subgroup, consider K1, K2 from NKH. Then K1H, K1 inverse is equal to H equal to K2H, K2 inverse. Now H equal to K2H, K2 inverse implies that H equal to K2 inverse H, K2, and hence K1 K2 inverse H into K1 K2 inverse is equal to K1 into K2 inverse H K2 into K1 inverse. Since we have K2 inverse H K2 is equal to H, this is equal to K1 H K1 inverse, which is again equal to H. Thus it follows that K1 K2 inverse is an element of NKH. Also, you should note that K1 into K2 inverse belongs to K because K is a subgroup. Therefore, NKH is a subgroup of G. Now we have the following result, which actually computes the number of distinct conjugates of H. First, we prove number of distinct conjugates of H induced by the elements of K, and then considering K equal to G, we will get number of distinct conjugates of H in G. Let H and K be two subgroups of a group G. Then the number of distinct conjugates of H induced by the elements of K is equal to the index of NKH in K. To prove this, let us denote the set of all conjugates of H in K by T and the set of all left cosets of NKH in K by S. Now we are to establish a one-to-one correspondence between T and S. Let us define F from T onto S by F A H A inverse is equal to A NKH. Since the elements in T may have several representations, so it is required to establish that F is one-to-one. For this, we have K1H K1 inverse is equal to K2H K2 inverse if and only if H is equal to K1 inverse K2 into H into K1 inverse K2 whole inverse. This is if and only if K1 inverse K2 belongs to NKH. Again, this is equivalent to the fact that the left coset of K1 determined by NKH is equal to the left coset of K2 determined by NKH. Thus, F is well defined as well as one-to-one. Also, it follows from the definition of F directly that F is onto, and hence the result follows. Now, as a corollary of this result, we have the following important conclusion. Let H and K be finite subgroups of a group G. G may be infinite also. If H is invariant under n elements of K, then H has order K by n conjugates by elements of K. Now we have this particular case, though this is very important in respect of applications. Let H be a subgroup of a group G, then the number of distinct conjugates of H in G is equal to the index of NH in K. Note that in case of conjugate of an element in G and conjugate of a subgroup H, in both these two cases, we considered elements from a group G. In a later module, we will introduce a new concept known as group action, and we show that both these ideas are particular cases of group actions. However, we will show that the conjugacy class equation gives us a result that if P is a prime number which divides order of a finite group G, then G contains an element of order P. G may be commutative or non-commutative. This result is known as Cauchy's theorem for finite groups, and we will prove this result in the next module.